Hello guys, I'll be starting the lesson right now. I'm sorry if my internet goes off because my internet's currently really slow right now, So today we're going to be reviewing what we did last time with mass percents, and we're going to learn something new called an empirical formula today. So those are the two main concepts we're going to cover today. So the first one's a review and the second one is something new. So for this week, just like the last 2 weeks, I believe, there's going to be 4 questions in a Google Forms quiz in the same place. It's called Homework 11. And I'll give you written feedback and post your grade on Google Classroom. On the last quiz on Homework 10, I'm sorry I made an error in the answer key. And thank you for pointing it out to me. I fixed it and your grade has been updated to show that correction. I selected the wrong answer during the homework, so I'm sorry for any inconvenience it caused you guys. And as always, if you have any questions, you can please contact me at this email below. So, like I said earlier, we're going to start off with a mass percent review, and then we're going to switch to finding empirical formulas at the very end. So, let's start with the review. I hope you guys remember this. If not, we're going to review it today again. So let's begin by supposing we have a compound with formula AB, where A and B are elements. They could be any elements. So one such example is we could have NaCl, where A is Na and B equals Cl. So this NaCl is table salt. So that's a compound. We could also have compounds like H2O, where A is H2 and B is O. So that's a compound. And we can even do this for compounds with 3 or more elements. So like we can have C3H6O. We can do it for compounds like these as well. This is just a general form, so it's easier for you to interpret. So I could give you a precise definition later on. So the mass percentage of A, like we talked about last time, is the mass of A over the total mass times 100. So it's this simple calculation down there. So let's go to the NaCl example because I want to talk about that today. So the mass percent of Na is the mass of Na over the mass of NaCl times 100. And that's basically all the mass percent is. And we similarly can do the mass percent of Cl, which is the same thing, except the Na on the top right here becomes Cl. So mass percent is basically a fraction. And then we multiply by 100. So this is our first question. So please put your answer, PM me the answer in the chat when you got it. So what is the mass percent of H in H2O? So I believe this is a different example than we did last week. It might be the same, but I changed the later ones so we didn't have a repeat. And the molar mass, everyone, I hope you know hydrogen has a mass of 1 and oxygen has the mass of 16. I would prefer you to give it in a decimal, but if you don't have a calculator, it's fine. You can give me the fraction as well. So I had a question that says, do you put H2 on the top or H? What's the total sum of H? But in this case, there's 2 hydrogen atoms in 1 molecule of water. So I guess it's still 2. Technically, you could put H2 on the top and do it the same way, or you could put H. Just know that H2 is not an element. The element is just hydrogen, but we have two molecules of hydrogen in a molecule of water. So I'll go over it. So the percent hydrogen by mass is the mass of hydrogen over mass of water times 100. So then what we have to do now is determine what is the mass of hydrogen and the mass of water. So we have noticed that we have 2 molecules of hydrogen. So it has a sum of 2. The mass of H2O, it's 2 times hydrogen. So it's 1 times 2 plus 16 is 18. And then we multiply it by 100. And our calculations give 11.1%. Make sure to multiply by 100 since we are converting it to a percent. So the answer is 11.1%. Yep. So now let's do the reverse problem and try to find the mass percent of oxygen in H2O. So please type your answer in the chat when you finish that. Here's the masses again. I'm sorry I didn't put the periodic table. That would have been a good practice for reading off a periodic table. Okay. I think I've given everyone sufficient time. So a shortcut way, since we just did the last problem, is notice that there's 100% mass in total. And then we could subtract the percentage by mass of hydrogen, which in the previous problem was like 11.1%. So we get like 88.9%. So we were able to do this just because there's only 2 elements in this compound. So we could do that subtraction because the mass percentage of hydrogen plus the mass percentage of oxygen should give you 100. So that's one possible approach that you could have done. The other approach is doing it the normal way. So mass percent of oxygen is the mass of oxygen, which is 16, over the mass of water, which we calculated in the previous one, is 18 times 100. And you also get 88.9%. So this is 2 ways that we can get the exact same solution. So I hope this is clear to everyone. Okay, so let's move on to the next problem. Sorry, I was answering a question in the chat. So this is an example problem. Please put your answer in the chat when you finish this. So this is calculate the mass percentage of hydrogen in carbonic acid, which is H2CO3. And carbonic acid is commonly used in bubbling drinks and sparkling wine. So it's in Coke, Sprite, and all of the sodas that I know a lot of people like. So I know this one's a pretty much harder than the previous one, since the the total mass would be a little larger. One thing I'd like to caution about is make sure to keep track of these subscript, this 2 and this 3. Remember from part 1, I told you that a subscript of 2 means that there's 2 hydrogen atoms in this molecule. There is no subscript for carbon, so that's 1 carbon. And there's 3 oxygens. And then after that, you're going to have to use the masses, which you could assume hydrogen always to be 1, oxygen 16, and carbon to be 12. And then hopefully you can okay. So I'll go over this now. So the mass percent by hydrogen is the mass of hydrogen. 2 times 1 is 2, because we have 2 atoms of hydrogen over, and each hydrogen atom has a mass of 1. And the total mass is, so the hydrogens are 2, the carbons are 12, and the oxygen, there's 3 times 16, that's 48. So if I did it correctly, remember the molar mass is 62. So we can have 62 times 100. And that's like 3.23%. Sorry for my bad handwriting. So 3.23%. Yep. So now it's a similar problem, but try to do it for carbon instead of hydrogen. So please put your answer in the chat. I left the total mass up here at 62, so it might be a little easier for you since we're doing the same problem. So, except we're looking at carbon now. So what is the mass percentage of carbon? Please put your answer in the chat when you have it. Okay. Since this is the same, I'll start going over it. So I hope that was sufficient time. So the mass percent of carbon So the carbon, we look at this category, it's just 12 over 62 times 100. And plugging that into a calculator gives around 19.3%, I believe. Yeah, 19.35, 19.4. And I believe that's the correct answer. Yep, 19.4, 19.3, depending on how you round. So let's do this problem one more time, but now let's do oxygen. So please type in the chat when you figure out oxygen. Okay. So let me go over it now. Mass percent of oxygen equals the mass of oxygen is 48 over 62. If you don't know, I got 48. We have 3 oxygen atoms, as we could see by this subscript, and each oxygen atom is 16 by the molar mass. So 3 times 16 is 48. And plugging it into our calculator, we get 77.4%. Yep. So that's how we do these types of problems. So now we're going to do a new type of problem that could be solved by mass percents. We talked about it last week, but we only briefly mentioned it, and this time I want to make it more clear and intuitive for you. So we want to know how many grams of carbon are there in 83.5 grams of formaldehyde, which is CH2O. So the first step to solve these problems is find the mass percent of carbon. And the mass percent of carbon in that molecule tells you how much percent of that molecule is carbon atoms. So then we multiply the total mass by our calculations. We multiply the total mass, which is 83.5, by our mass percent in decimal form, and then we get the grams of carbon in the molecule. So please put your answer in the chat when you have it. I'm sorry I did not give you a periodic table. So formaldehyde, carbon is 12, hydrogen is 1, and oxygen is 16. Actually, for this part, I'll guide you through this calculation, and in the next two, I'll leave it as an exercise. So the first thing we want to do is do the mass percent of carbon. So the mass of carbon is 12. The total mass is, so there's 2 hydrogens and 1 of everything else. So that's 12 plus 2 plus 16. That's 30. So 12 over 30. So, and then times 100. So putting that in a calculator, we get 40%, which is a nice number. So 40% of this mass right here is the grams of carbon. So what we do is we do 83, we take the total mass and we multiply it by carbon in its decimal form. So 40%, the decimal form is 0.4. A common mistake is putting 40 right here, and then it gives a really large number, which is incorrect. So remember to change it to decimal form, and then we get 33.4 grams. So these problems are like applications of mass percent. You do the same thing we've been doing, and then you take the total mass and you multiply it by the decimal form. So try it for this one. It's the same problem, but do it for hydrogen instead. So PM me in the chat when you got it done. We can erase all of that. And the molar mass is 30 still, yeah. I know these calculations can be a little more tedious than previous ones. Okay. So a lot of people have gotten it correct, so I'll share the solution right now. So this is a similar, the first thing we need to calculate is the mass percent of hydrogen. So that's what we need, the mass percent of hydrogen. So to calculate the mass percent of hydrogen, we take the mass of hydrogen, which is right here, 2, and then we take it over the total mass, which is 30, and we multiply it by 100. And we get like what did we get? It's like 6.7%. Now we take the total mass, 83.5, and we multiply it by this in decimal form. So if you don't know how to convert to decimal form, just divide the percent by 100. So it's 0.067. So this is the decimal form, and you get 5.6 grams roughly, or 5.57 grams. Yep, and that is the correct answer. So I hope you guys are getting the hang of it, because you're gonna have a homework problem exactly like this one on the homework today. So there's one more question I want to ask. Now let's do it for the oxygen atom. So please put your answer in the chat when you solved it. So we're going to do percent oxygen instead. So I'm going to erase the parts that are different. And I'll give you some time to try to solve this one out. I'll give you a few more seconds to try to solve this problem. Okay, so I'll solve it now. So percent oxygen, you have to look at the mass. The mass is 16 because there's one oxygen atom and each oxygen atom is 16. So 16 over 30 times 100 is 53.33%, 3%, and changing it to a decimal point is 0.533. And then the final answer you get around 44.5 grams. So that's the answer you should get. And yep, that's what I got earlier. So now we're going to talk something new for the last 15 minutes of class. We're going to find empirical formulas. So the percent composition. So the thing we just did was the percent composition. So we found like how much percent of the mass was carbon atoms, how much percent of the mass was oxygen atoms using the molecular formula. But now, if we have the percent compositions, we can go back and deduce an empirical formula. So you might be wondering, what is empirical formula? So it's a formula for the compound with the lowest integer subscripts. So it's with the smallest integer subscripts, such that 2 are not a multiple of 1. So here's an example, H2O2. So you look at the subscript, and each one is a factor of 2. So you can divide by 2, so it would have an empirical formula of HO. Note that a compound HO does not exist, but it is an empirical formula since it is a compound written with the smallest integer subscripts. Another example is C6H12O6. Notice that all of these subscripts can be divisible by 6, so it has an empirical formula of CH2O. I'd like to tell you guys that if a compound is in like CH3O6, although there is not a subscript behind the C, it is implied to be a 1. And the greatest common factor of 1, 3, and 6 is 1, so you cannot reduce it any further. So this is the empirical formula. So there's no simpler term for this compound, CH3O6. But in this case, in C6H12O6, all of the subscripts are divisible by 6. So we can reduce to CH2O. So note that. So let me clear the screen. So now we're going to use the percent compositions to find the empirical formulas. So this one's going to be me working through the problem with you guys, and hopefully you understand. If you have any questions along the way, please type it into the chat so I know if you don't understand anything. So the strategy we're going to use to solve these problems would be a 3-step strategy. So the question is, so in the lab, we determined that a compound consists only of nitrogen and oxygen. And we realized there's a 0.483 grams of nitrogen and 1.104 grams of oxygen. And we want to find the empirical formula of this compound. So our first step would always be convert grams to moles. That's our key step, grams to moles. So we start off with 0.483 grams of nitrogen. And we look at the periodic table here. So it's 14 grams of nitrogen is 1 mole nitrogen. So we did this like 2 weeks back where we converted grams to moles. And the way we're doing that is the molar mass. So I hope you guys remember the molar mass helps us to convert from grams to moles. The reason being the grams of nitrogen and the grams of nitrogen cancel out. And then once we do this calculation, which is 0, we get 0.0345 mole of nitrogen. So we converted the grams to moles. Now we do the same thing for oxygen. So 1.104 grams of oxygen. We look at the molar mass, which is basically 16. And then we could cancel it out. And when we put it into our calculator, we get 0.069 moles of oxygen. So that's how we do our first step. So I hope everyone understands how this first step is done. We convert grams to moles. Okay, and our answer key agreed with that. Okay, good, everyone understands. Let's clear what we have so far. So this orange stuff is this thing we just discovered, grams to moles. So now our step 2 is divide both numbers by the smallest number. I have some people asking, is it into O? It is not into O. So please bear with me. These next 2 steps will be pretty fast and we can get the answer really quickly. So we divide the mole by the smaller number. So we look at these 2 numbers, 0.0345 and 0.06900. And using your higher math skills, you realize this number right here is the smaller number. So we divide both of those numbers by 0.0305. So we divide by 0.0345. So we get 1 for nitrogen and we get 2 for oxygen. And this step was pretty easy. So that's all step 2. We divide by the smallest number. So the first step, we converted grams to moles. The second step, we divide the moles by the smallest number. And that's what I got in answer key, so that's good. So now, once we get the number, we get 1 for N and 2 for O. Sorry, this is a typo. It should not be mole. So now we just use these numbers as the subscript. So N, O, and 2. Because O gets a 2 and N gets a 1. So the empirical formula is NO2. So that's all we do. It's 3 simple steps. The first one is changing these grams to moles. The second step is dividing by the least number of moles. And the third step is using those numbers we get as our subscripts. So that should be fairly not too bad, I hope. But there are some special conditions for step 3. So for step 3, what if we get fractional numbers? That's going to be bad, and we need to find a way to solve it. So for example, if we get in step 3, we get 1 for carbon and 1.67 for hydrogen. This is the incorrect formula. We do not have CH 1.67. That's bad. It is not acceptable. We need whole numbers. We cannot have like 1.67 of a hydrogen atom. That just does not exist. So our solution, we can multiply both numbers till all numbers are integers. So notice that if we multiply both of these by 3, we can get 3 carbon, and 1.67 times 3, that's 5.01 hydrogen. Now, 5.01 is really close to 5. So we could just assume that's the same as 5. It might be due to like rounding errors. So we'll have, and then we'll use those numbers directly, C3H5. So that's what we do. It might be a little off, like 5.01 or 5.02. If it's that close, we can assume that it's 5. But like 1.67, we can't assume that's 2. That's just too far away from 2 to assume it's 2. So you just start multiplying it by numbers and waiting till you see that both of them are whole numbers. So that's what we wanted. And the reason I multiplied by 3 is 1.67 is really close to 5/3. And notice if you multiply by 3, the fraction goes away. So that's why I multiplied by 3. Multiplying by 1, 2, or 4 really doesn't do anything. You'll still have fractional numbers for the hydrogen. So here's another example. This is not CO2 in 1.33. That is completely wrong. You notice that this is around 4/3. So you multiply everything by 3. And you get 3 carbon, 6 oxygen, 4 nitrogen. So C3O6N4. The order really doesn't matter for which way you put them of the elements, but carbons are usually first if they're present. So that's some condition steps. Like, I don't think we're gonna see too many of these weird ones, but just in case, like in your honors chemistry course at school, you might have some fractions or decimals. You just multiply all the numbers until they're all integers. Okay, so we're gonna end class with this last problem. We won't get to the next problem because we're out of time, but I would like you to do one problem with you guys. So please put your answer in the chat when you have it. So this is one problem, and you have to do all 3 steps. So assume the mass of carbon is 12 and the mass of oxygen is 16. So if we have 6 grams of carbon and 16 grams of oxygen, what is the empirical formula? So to help you, step 1 is grams to moles. Step 2 is divide by least number of moles. And step 3, sorry for my bad handwriting, use them. In empirical formula. I'm abbreviating it as EF since it's kind of hard writing. So let's see what you guys got. And remember, to convert grams to moles, you use stoichiometry and use the molar mass to convert each grams to moles. Since we're kind of out of time, I'll start this one. I hope this one didn't have any nasty fractions in step 3, but okay, let's start. We start with 6 grams of carbon, and by the molar mass, 12 grams of carbon is 1 mole of carbon. So that's 0.5 mole carbon. 16 gram oxygen. 16 gram oxygen, 1 mole of oxygen. That's 1 mole oxygen. So we have 0.5 and 1. So in step 2, we choose the least number of moles. So we divide by 0.5. So carbon to oxygen, we have 1 to 2. When we divide, .5. So 0.5 divided by 0.5 is 1 for carbon, and oxygen 1 divided by 0.5 is 2. So in step 3, we just use them. So carbon gets a subscript of 1, and oxygen gets a subscript of 2. So we realize that this gas is carbon dioxide, which is what humans exhale due to the using of energy in cellular respiration. So I hope this wasn't too hard. So to recap, we first started with 6 grams. We converted grams to moles using molar mass, and we get the relative moles. Then we divide the moles by the least number, which is 0.5 in this case, and we got carbon 1, oxygen 2. And then we use that for our subscripts here. So that was how this process went. I did prepare one last one, but we don't have time today. We're going to probably do that next week, hopefully, and get to it. So to recap, for our homework today, we have 2 mass percent review problems on the homework, and there's 2 finding empirical formulas. I think they're relatively easy, so I hope that you can do it after learning today. There's 4 questions, and if you have any questions, please contact me at this email, and thank you for attending class today. Hope to see you next week. Hope you guys have a wonderful rest of your week. Thank you, everyone.
Thanks. Bye.
Bye.